All right, welcome to The Explainer. Today we're diving into something that sounds like it's straight out of a sci-fi movie, building microscopic mazes. And no, these aren't for mice. We're talking about mazes designed to trap light, cool down our super hot electronics, and even create clean fuel, basically out of thin air.
So let's just start with a really simple but kind of powerful question. We all get what a maze is, right? For a person, a mouse. But what if you could build one for something you can't even see? Something like a wave of light or heat.
Well, for one thing, you could trap it. Just imagine a beam of light hitting some kind of structure, and instead of just zipping right through, it gets forced to bounce around. Its journey totally delayed, basically held captive until you decide to let it go. Or how about this? You could build a maze to guide it. Think about the heat just pouring off your computer's processor when you're pushing it hard. What if you could build this tiny, invisible labyrinth that actually steers that heat away from the sensitive parts, spreading it out so it can cool down without causing any damage?
And maybe the most powerful idea of all, you could build a maze to put that energy to work. A maze that could grab and concentrate sunlight exactly where you need it most, supercharging a chemical reaction to create clean fuel from, get this, little more than CO2 and water.
Look, this isn't science fiction anymore. This is the real, core idea behind a brand new technology called quantum maze interfaces. And believe me, it promises to give us a whole new level of control over the energy all around us. Okay, so what is a quantum maze interface, really? Well, at its heart, it's a surface that's been patterned with this incredibly intricate maze at a microscopic level. The quantum part, that's because we're manipulating energy at the scale of its most fundamental waves, like photons for light. It's like scientists are becoming landscape architects, but for energy. They're designing these tiny mazes that bridge that weird quantum wave behavior with real-world effects we can actually see and use. Pretty cool, right? So, that leads to the next big question. How in the world do you design a maze for something you can't even see? It's not like you can just, draw some walls on a piece of paper. It's way more subtle and, frankly, way more clever than that. Turns out, it all comes down to three main design handles, or controls, that you can use. First up, you've got path count. Basically, you just add more loops and junctions, creating more ways for a wave to get sidetracked and delayed. Next, you can play with the path lengths, so you create all these different detours of different sizes to really fine-tune that delay. And finally, and this is where it gets really wild, you have boundary twists. This means using special surfaces that can actually flip a wave's properties around as it bounces off. Super clever. Now, you might be wondering where they even get the ideas for these crazy complex designs. It's not just from abstract math. The inspiration actually comes from biology. As this quote here points out, scientists are taking their cues from nature itself. They recently found these unique, kind of helical tube structures inside certain bacteria. And those elegant, natural forms, they're the perfect blueprint for creating mazes that are incredibly complex, but not just a random mess. Okay, so we've got the toolkit. Let's see how this all comes together to build three amazing real-world devices. This is where the theory really hits the lab bench. First on the list is a photonic storage device. Now, the problem here is pretty simple. Light moves insanely fast. And for the next generation of computing and communications, we desperately need a way to slow it down, to trap it, to create a kind of optical memory buffer. And the solution is brilliant. It's a maze made of these microscopic grooves etched right onto a surface. And each groove is tiny. We're talking about half the wavelength of the light you're trying to trap. So when light comes in, it's forced to bounce back and forth inside these grooves, which just massively slows down its overall journey. Think of it like turning a superhighway into a winding, scenic country road. And what's even cooler, you can apply a voltage to tweak the trap in real time. And this chart really shows you just how ambitious the goal is here. Yeah, we're talking about nanoseconds, which I know doesn't sound like a lot, but in the world of optical computing, that is an eternity. The goal is to jump from a baseline of just 10 nanoseconds of delay all the way up to a target of 50, and maybe, just maybe, a stretch goal of 200 nanoseconds. That's a 20-fold increase. It's a massive leap in capability. Okay, next up, they're tackling a problem that pretty much all of us are familiar with: heat. Every single powerful electronic device, from the phone in your pocket to a massive data center server, generates these little hot spots that kill performance and can eventually cause the whole thing to fail. So the old school solution is just to slap a big block of copper on it to suck the heat away.
But this Maze-Cool device, it is so much more elegant. It uses a super thin, perforated sheet of something like copper or graphene, and this maze isn't random. It's specifically designed to guide the flow of heat itself, which at this tiny scale travels as little vibrations called phonons. It steers those vibrations away from the hotspot, spreads them out, and lets the device cool down way more efficiently.
And get this, the performance target here is just staggering. A potential temperature drop of 35 degrees Celsius. Now, to put that into perspective for you, that's the difference between a processor that is red hot and dangerously overheating and one that's running at a perfectly safe, optimal temperature. I mean, achieving this would be an absolute game changer. It would let us build so much more powerful and compact electronics without having to worry about them literally melting. All right, for the third device, the team is aiming to solve one of the biggest holy grails in clean energy. How do we efficiently use sunlight to create fuel? It's a process nature has mastered, of course, but our artificial versions, well, they're still lagging way, way behind. So enter the BioMaze. This is a tiny microreactor that uses that exact same light-trapping trick we saw in the first device. It creates a photonic maze right next to a catalyst or a biofilm, the thing that actually does the chemical reaction. By trapping the light, it increases what's called the dwell time. That's just the amount of time the photons hang around and interact with the catalyst. And by doing that, it dramatically boosts the efficiency of the entire fuel creation process. Okay, now for what is, I think, the most mind-bending part of this entire research. So far, we've been talking about the layout of the maze, the paths, the loops. But what happens when you build a maze with a topological twist baked into the very fabric of its boundary? To really get this, think about a simple cylinder, like a paper towel tube. It's got a clear inside and a clear outside, right? That's what scientists call an orientable boundary. But now picture a Mobius strip, that famous loop with a half twist in it. If you trace its surface, you'll find it only has one continuous side. That's a non-orientable boundary. And building an optic with that strange property lets you manipulate waves in really powerful and frankly bizarre new ways, like being able to controllably flip their phase. Now, the inspiration for this stuff comes from a really deep, almost esoteric place in theoretical physics. The researchers saw this parallel between how the waves were behaving and a wild concept called ER equals EPR, which connects wormholes with quantum entanglement. But, and this is the absolute crucial point you see in the quote, they are being super clear about this. This is an analogy. They're using the math as an inspiration to see what they can do with waves. They are not claiming they built a tiny wormhole on a lab bench. So what's the actual practical outcome of sending light through one of these twisted mazes? Well, it's pretty astounding. You can take a single, simple beam of light, pass it through one of these non-orientable optics, and create an image in the distance that looks, for all the world, like it came from two separate, distinct light sources. It creates this stable, two-lobed profile, effectively a shadow duplication from just a single beam. It's wild. Okay, so let's take a step back and zoom out for a second. What does all of this, the light traps, the heat spreaders, these crazy twisted optics, what does it all really add up to? What this research is really giving us is an incredibly powerful new toolkit. This is so much more than just 3 cool devices. It's a fundamentally new way of thinking about materials. It proves that by engineering shape and structure and topology at the smallest scales, we can unlock brand new ways to control heat, light, and even chemistry. So I think the big takeaway here is this. We're moving past just using the materials we find lying around in nature. We are actually learning how to engineer them from the ground up, to literally write new rules for how energy behaves in our world. And that leaves us with a final and pretty profound thought about the future we can now start to build. So, what should we create next?